Hello, students. So let us continue the topic as we had earlier. So we learned about the electric potential difference, and we learned about the electric potential energy for a system of charges. So you learned that to bring a charge or to bring charges or to assemble charges at a specific part of a specific portion of a space, you need to do work against the electrostatic forces when you bring the charges from infinity towards that specified portion of the space. So that work you have done, that is equal to the potential or electric potential energy of that system. So we have learned about that. Now today we shall be learning about unit of a different unit of energy. Okay, so previously you have learned that the unit of energy or unit of work done is joule or calorie or something like that in different systems of units. Okay, in SI units you know that the unit of energy or work is joule, but we are going to find some other unit of energy that is an important thing. Okay, so why is it important? So let us learn this. So that concept is electron volt. That concept is electron volt. Electron volt. So what is electron volt? Electron volt, or you can name it EV. The E should be small and V is bigger, the capitals. Okay, so it is a unit of energy. You can write it is a unit of energy. So let us define it. So first of all, you have learned that it's a unit of energy. So when an electron is projected through a potential difference of 1 volt, okay, I'm just coming direct to the definition that when an electron is projected through a potential difference of 1 volt, okay, so there are 2 points in space like point A and B. The potential difference between them, let it be V and VV, the potentials. So VB minus VA is equal to 1 volt. Why did I write like this? I took the mode? Because I don't know if VA is greater or VB is greater. So I took the mode. Okay. So when an electron is projected from this part of the space to this part of the space, so an electron is getting projected through a potential of 1 or potential difference of 1 volt. So in doing so, either it gains some energy or lose some energy, and that amount of energy is known as electron volt. Okay, that amount of energy is known as your electron volt. So coming straight to the definition, when an electron, so you can write like this. So I hope that you have understood the concept of that electric potential. So an electron is projected. Let me see if it is visible or not. Yes, it is visible. So an electron volt is a unit of energy, and the definition is when an electron, you can write like this, when an electron is projected through when an electron is projected through a potential difference, a potential difference, when an electron is projected through a potential difference of 1 volt, then the change in its potential energy in its potential energy is called an electron volt. Simply write like this. So when an electron is projected through a potential difference of 1 volt, then a change in its potential energy comes. Either it has lost some energy or it has gained some energy. So that amount is called electron volt. That amount is called electron volt. So 1 eV, it is a unit of energy. 1 eV is equal to, or the potential energy, you can write it like this: the potential energy U is equal to QV. Okay, that is the change in the potential energy. So what is Q? The electronic charge. You know that the electronic charge is 1.6 into 10 raised to the power minus 19 coulomb into, what is the voltage difference? It is 1 volt. So what is U? 1.6 into 10 raised to the power minus 19 coulomb volt. Okay, this thing get multiplied with 1, we get the same thing. So U is equal to 1.6 into 10 raised to the power minus 19. This thing is joule. This thing is joule. Okay, so what is U? It is 1 electron volt. So the value of 1 electron volt is this much. The value of 1 electron volt is this much. You can actually see that it is a very small unit of energy. Okay, joule is the unit of energy, so electron volt is also an energy, so it is very small. See, it is 1.6 into 10 raised to the power minus 19 joule. That means 1.6 over 10 raised to the power 19. So it is a very small amount of energy, but it has a very great significance in the field of atomic physics as well as nuclear physics. Okay, so you will find it often in atomic physics. Okay, so you can actually see that it is a very small unit of energy, but in atomic physics it is a very great significance. Okay, so we have learned the concept of electron volt. So if the question arises, what they can ask you, if an object has electronic charge or charge as a negative charge, you can write like this: as a negative charge of 5 coulomb. Okay, 5 coulomb is the negative charge or a positive charge, I don't, that doesn't matter here. It is projected through a potential difference of 5 volt. Then it asks you what is the potential energy change of that object. So you will write it like this: that charge multiplied that voltage difference, which will give you 25 joule. Okay, it can ask you in electron volt also. So from here you can see that 1 joule is equal to 1 electron volt over 1.6 into 10 raised to the power minus 19. Okay, this is the value of 1 joule. You can actually put it at this point. These things go over these things, it is equal to 6.25. So 1 joule is equal to 6.25 into 10 raised to the power 18 electron volt. I hope it is right. Let me check. So 1 divided by 1.6, it is 0.625. 1 divided by 1.6, yes it is. So either way you will get the result, but you have to remember this thing: conversion can be done later, but you need to remember the value of 1 electron volt. Okay, so as it is a very small amount of energy, in order to denote it as some larger amount of energy, we use 1 mega electron volt, 1 kilo electron volt. Sometimes we use 1 milli electron volt to denote some even smaller energy, 1 micro electron volt, something like that. So what is 1 mega electron volt? If anyone asks you in the exam what is 1 mega electron volt, the value of 1 MeV. Okay, this is not milli, M is capital here. So what is this? So 10 raised to the power 6, the value of mega is 10 raised to the power 6, multiplied, you write the value of electron volt 1.6 into 10 raised to the power minus 19 joule. Now these things get multiplied, we will get 1.6 into 10 raised to the power minus 13 joule. Okay, or in place of this you can write it 1.6 into 10 raised to the power minus 13 EV, whatever you can write. Okay, so not like this, you can leave electron volt as we are required to do it in electron volt. So the conversion thing comes later. Okay, so we have learned about the concept of electron volt. Now we shall be jumping to the last concept of electric potential. That is, we are going to place an electric dipole in a uniform field. Okay, we are going to place an electric dipole in a uniform field with some angle. So potential energy, the heading is potential energy of an electric dipole in a uniform electric field. Okay, in a uniform electric field. So you are given a uniform electric field and you have put together a dipole. So as we have known from earlier classes, previous classes, what is a uniform electric field? At a part of space, or how are you going to represent a uniform electric field? In a part of space, you are going to build or construct some parallel lines. Some parallel lines. So this is a uniform electric field. These lines should be parallel. Make these lines straight and parallel so that you can denote it as a uniform electric field. Now you have put a dipole. Here, and that dipole makes an angle theta. That dipole makes an angle theta with the electric field lines. Okay, the dipole makes an angle theta with the electric field lines. So if it is a dipole, it should have a positive charge, it should have a negative charge. Build like this, some plus q, just extend it a bit further. Okay, it is plus q, the positive charge is here, the negative charge is here. You can also bring the positive charge here, the negative charge there. It does not affect the derivation. So as we know, the distance between the two charges in a dipole is 2a. This distance is 2a. This distance is 2a. So a positive charge is forced along the electric field lines. So you can actually see, if it is an electric field and this is a positive charge, you can actually see a force is being exerted on the positive charge in the direction of electric field, and in the same case a force is being exerted in the opposite direction of electric field if there is a negative charge. So the force for negative charge is to this direction and the force on the positive charge is to the right direction. So what is the force on charge plus q? It is plus qe. What is the force on charge minus q? It is minus q. You can actually see that. Now you can see that these two forces are equal in magnitude but in opposite direction. That means they form a couple. They try to twist it. Just like while starting an automobile, using a key, not that pressing the button type key. When you put a key into the keyhole and just twist it, you can actually see that key is this thing, and you apply a force on the thumb, apply a force on the key from the thumb on the upper portion of the key, and the index finger is on the lower portion of the key, and you try to produce a twist. That is the same thing here. Okay, it is trying to produce a twist. Okay, so we are going to calculate the torque. Okay, the torque, the twist is known as torque. We are going to calculate the torque from this situation, and then we shall be trying to find out the work done. We shall be trying to find out the work done. Now, let us write some statements. So, let us place, or let us consider. Okay, we can write like this. Let us, today is very humid day, of course. Let us consider a dipole. Let us consider a dipole is placed in a uniform electric field. Uniform electric field. So we have placed an electric dipole in a uniform electric field. Okay. So let it makes an angle theta with electric field lines. With electric field lines. With electric field lines. Okay. So you can also write like this, then that let it be aligned at an angle theta with the electric field lines. Now, so since it is an electric field plus q charge, a force plus QE acts on plus Q to the right from this diagram. Okay, take reference from this diagram, according to this diagram, and a force minus QE acts on minus Q to the left. They are equal in magnitude. You can write they are equal in magnitude. They have the same magnitude but opposite direction. But opposite direction, which makes them a couple. Which makes them a couple. So they act like a couple. They act like a couple. Act like a couple. So let us just continue. They act like a couple. So since they act like a couple, a torque is going to get out of it. Okay. When you act like a couple, productive things come out in life also. In this case also, since the two forces are acting like a couple, so they are going to give birth to a new thing, that is a torque. A torque will come into the act. A torque will come into the act. So what is the value of that torque? What is the value of that torque? So torque tau is equal to force, either of that force. Okay, you can write this force or this force, either of that force, either force. Okay, either force. So you have two forces. What is the forces? One is QE and another is minus QE. We can take either of that forces into multiply with the perpendicular distance between them. Perpendicular distance between them. Okay, so you are going to take one force and try to multiply it with the perpendicular distance between them. So what is the perpendicular distance between them? It is actually this thing. The perpendicular distance is actually this thing. This is the perpendicular distance. So how are we going to find that perpendicular distance? How are we going to, since this angle is theta, this is also theta, so write it like this. This is theta. So how are we going to calculate the distance? Let us name it as AB. AB. Okay. So write it like this: QE, either of that force multiplied AB. So our mission now is to find AB. So how are we going to find AB? So from the triangle you can actually see AB. Let it be point C. It is 2A. It is theta. I think it is visible to you. Since it is a right angle triangle, you can actually write, you need to find AB. Sin theta is equal to AB upon AC. Since AB is needed, it is AC sin theta, and you know the value of AC, that is 2A sin theta. Okay, so AB, or the perpendicular distance, is 2A sin theta. So QE into 2A sin theta. 2A sin theta. Now you need to do some arrangement like we always do. So Q into 2A into E sin theta. Q into 2A into E sin theta. So if you can actually remember the concept of electric dipole, you can see that it is charge multiplied the distance between the two charges in an electric dipole, and that gives birth to the electric dipole moment, PE sin theta. That is your tau. Okay, if it is asked that how much is the torque acting upon that dipole in that uniform electric field, you shall be writing torque tau is equal to PE sin theta, or torque tau is equal to P cross E. It is a cross product. Okay, so when it is a cross product, P cross E is equal to PE sin theta. You can actually write that. So this is the amount of torque that is acting upon that dipole if it is placed in a uniform electric field. So this is called torque, and this is the formula. Now it is not over, because we are going to find out the potential energy of an electric dipole which is kept in a uniform electric field. We have come up to torque. Okay, so I have to make some place for our, so I think you have noted this. So I have found out torque, that is PE sin theta. Torque is equal to PE sin theta. Okay, now if it is twisted through a potential difference of, or sorry, if it is twisted through an angle of d theta, if it is twisted through an angle of d theta, so a small amount of work is done. Okay, now when as you know from the concept of work energy theorem, work is force times the displacement. Similarly, in rotational motion, work is the angular displacement times the torque. So in this case also, if dw is the work done, if dw is the work done, by aligning, by twisting, okay, by twisting the dipole, through an angle d theta, so it is twisted through an angle d theta, then a small amount of work is done, that is dw. So what is dw? Then dw is equal to tau d theta. So I see that it is visible. So if now put the values of these things, PE sin theta d theta. Since it is a small amount of work done, now we shall be calculating the total amount of work done when a dipole is brought from an alienation of theta 1 to an alienation of theta 2. Okay, so W is equal to integration over PE sin theta d theta. So what is that angle range? It is theta 1 to theta 2. So actually initially it was having an aligning direction of theta 1 with the electric field. Now we have done work and we have just at this point it was theta 1. Now we have tried to twist it and brought out to this angle. This is called theta 2. So some work is done. Since P is constant, E is also uniform, so they make it out of the integration. So they make it out of the integration. We are left with sin theta d theta, theta 1 to theta 2. As we know, the integration of this integral is PE cos theta or minus PE cos theta from theta 1 to theta 2. Okay, so I hope that you got it, as we need to remember some concept from our integral part. So what is work done when you put those values, that is PE cos theta 2 minus cos theta 1. This is your actual formula. Now if you try to multiply this thing, so you will see that W equal to PE cos theta 1 minus cos theta 2. This is your actual formula of work done. So if you are with an angle theta 1 and you try to twist the dipole to an angle of theta 2, so the work done is PE times cos theta 1 minus cos theta 2. This is your formula. This is your required formula. So I think you should not up to this point, and some important things remain. So just take a screenshot, or if you are noting, then it is a good thing. So I think that you have written all these things. Now you are concerned about that formula and some more things. Okay, going to bring in some cases from this formula. Very easy things. Now if theta 1 is equal to 90 degree, that means it is like this. Our dipole is like this. It is making an angle 90 degree with the electric field lines. So if theta 1 is equal to 90 degree initially, then what is W? It is PE cos 90 minus cos theta 2. Now if theta 1 is 90, let that theta 2 is equal to theta. Okay, that is a general thing. So now what is work done? It is PE cos 90 is 0, so we get minus PE cos theta. Now if initially it is making an angle 90 degree and finally it comes to an angle theta, so you can actually see that the formula gets modified minus P dot E. It is also a formula for work done. If given that initially it is making an angle 90 degree with the electric field lines, this is also a formula. Now some other things can also be taken out, like if it asks what is the zero energy of that dipole, what is the stability point of or stability angle of that dipole. But up until then you can actually not up to this point, and we shall be considering problems in the later lectures regarding this topic, 1 to 2 problems. So up until then, take care, practice more, and if you have any doubts you can ask in the comment section. or I have given you the contact details. So let me take out the camera to a little higher position. I have to stoop. So if you have any doubts, you can ask me in the comment section. You will get a good response. Now, if you have any doubts regarding numericals also, even if it is not related to this chapter for class 11th and 12th, you can ask me also there. I have provided you in the description box my contact details. Share our lectures with your friends, subscribe to our channel, like our videos, and up until then, take care, practice more power to you. See you.